All right, Physics Reaction 61. Today I did a search for physics lecture notes and limited it to this week. And found this one. Let's see what we got. Skipping ahead here.
Physics video lecture. Physics 105A video lecture 9. We're going to review a bit, but I'm going to set up that problem that we left off with last time. This is really getting into the great material, and we're going to turn this into a couple excellent homework problems as well.
Cool.
So here's where we are. We have conservation of energy, and then we learn to separate variables because the x dot is a dx dt.
Cool.
And we end up with t equals plus minus integral dx prime root 2 over n e minus u of x. You're just treating this thing algebraically.
So it's interesting. It seems like this is review, right? So the students have probably already seen the notes that his app was just covering. But I love talking about this, right? Because, you know, as long as you're talking while you're writing in these video things, I think it's totally fine because the students can try to maybe make sense of what you're doing. And then when you reveal by moving out of the way, I think it's awesome, actually. So this is a really interesting... So when I saw Physics 105A, I thought, well, probably college level, and 105 usually means lower level, but putting dots over your X's, I'm not sure what level this is, actually. So this is actually a really, really slick thing to do, right? So you write this as dx dt squared, and then you solve for dx dt, which has to put in the square root. And then you say, oh, well, I can just integrate both sides because if you integrate this dt, you just get, oh, I see. Sorry, he flipped it over. He solved for dt dx. So he flipped it over. And sorry, mathematicians, but derivatives are just fractions. So he solved for dt dx, and then he integrated dx, and he gets t, right? And so that's why there's this x integral here. I'm not sure if that's a prime or not. Let's go back and listen to that. The rest of it 2 e minus u of x. Yeah, I'm not sure what that little mark there is. Let's go back and listen.
Dx prime
What is a prime?
2 over n e minus u of x. You're just treating this thing algebraically.
Okay, so this should be a prime too, right? The other x.
0, x.
Yeah, so this should be an x prime right here.
So that's the method that we use, and actually I set up as a homework problem to solve the basic free fall problem. Okay.
That's cool.
And
I love this too, this plus minus.
Back to that, but from
It's because of the square root.
Since we have this dx dt is equal to, and we'll go ahead and solve for it, plus minus 2 over m e minus u of x. Since we had this expression as well, we were able to introduce the idea of turning points given a certain type of potential energy.
Oh, very cool.
So right under here,
The turning points, of course, are crazy for the integral.
right under here we can imagine that we have a u of x, function of x. And this time I'm going to draw a non-symmetrical one,
Oh, cool.
like that. Okay.
Awesome.
X go out here a little further. Okay, so I deliberately made it, in fact, let's make it even.
So I see where he's going. This is super cool stuff. But I guess what's interesting to me is that to get the students to realize that when all of the kinetic energy is turned into potential energy, that it's got to turn around, is something that you could have done well before getting into this level of detail, right? So where the potential energy, where the energy is entirely potential energy, oh well, the kinetic energy came to zero, so it must stop there, right? That's the basic idea. But mathematically, it shows up. You can't see it; it's behind his head here, but it's the same thing as this denominator here, right? He's just trying to find when would x dot be zero. So he's going to, do the same thing. But so it's really two different approaches, right? One is, oh, hey, you know how energy works. If there's no kinetic energy, it must be at rest. But here it's literally looking at the speed of the particle. And of course, we're going to end up with the same thing. And he's going to get what I'm assuming is a cool graphical way of saying it.
Less symmetrical. This is going to be a really classic one anyway. That we will see quite a bit of. Here's x.
My guess is it's going to go, right? That's what my guess he's going to draw.
U of x. Suppose our potential
Nailed
looks
it.
like that. I'll write down what the function is for that. Could be a number of them. And this comes up against the axis as x goes to infinity.
Very cool.
And so there's a potential with a local minimum at x0.
So again, I don't know who the audience is. I don't know who has seen this before, but that curve is super famous, right? But it's actually famous when you take the 6 degrees of freedom two-particle problem, turning it into 3 degrees of freedom, where you're basically looking at from the center of mass to a fictitious particle, and then you get rid of another degree of freedom when you say, oh, you know what, this is only going to stay in one plane, so it's only 2 degrees of freedom. And then you realize, oh, wait a minute, if we actually have some fun with the angular momentum, we can get this centrifugal barrier, which is what this is. And then you're solving a fictitious problem, a problem that doesn't exist in real life, but its results can then be, you go from the one variable, the fictitious variable you solved, you go back to 2 and then 3 and then 6, and you have the whole solution of the whole problem. So it's interesting that this is a famous potential energy, but it's not real, right? It's for this fictitious problem. So I think it's interesting to jump to this. Again, I don't know what his student's background is, but this is a perfectly legitimate potential energy to investigate from this perspective, right? He's going to have these bound states when his energy is less than 0, and he's going to have these unbound states when it's above. And, orbits and all of that stuff is where this stuff comes from, which is super topical, super interesting. But it's interesting to just kind of slap it right down. So I'm curious to see how he nuances that.
I have to call it something. Not to be confused with that x0. So that's my local minimum now. And if my energy is equal to u of x, then this expression is 0, therefore the speed is 0, the velocity is 0. And so let's go ahead and have an energy here, E, and I'll draw the little dotted line across.
Sometimes my students struggle with negative energies, right? They seem not to care about negative potential energies, but negative total energies really freak students out sometimes. So the bound states he's looking for, the 2 turning points that he's looking for, the way he drew his potential energy has to be at negative energies. Of course, it all has to do with where you define your zero potential energy.
And you can see that there is a minimum x and a maximum x.
Cool.
Between which the motion occurs. Okay, there's a minimum x and a maximum x. That's where the velocity vanishes. Those are the turning points. So yeah, it doesn't have to be a positive or a negative energy. In this case, it's a negative energy.
So it's great that when he's drawing, you can't help it. You're going to block stuff. But I like this gigantic pointer because it enables him to really call out things without being in the way. So that's really cool. Also, by the way, super awesome focus, right? I haven't seen any autofocus problems. It kind of looks like this camera's far away. I'm not sure if the microphone is attached to the camera or if he's got a microphone on his shirt. It doesn't look like it, but the sound is great. The video is great.
Because of where this thing is located. So then you could talk about an oscillation, and you could say I'll go between x min and x max. So for motion restricted to x min less than or equal to x less than or equal to x maximum. For that motion that's restricted there, you guys can always just imagine a ball rolling between here, something sliding between here without friction, back and forth. That's what your oscillation is in a potential well. So for such a motion restricted like that,
So ball rolling in a well. So I put a lot of thought into this one time when I was realizing that a ball in a parabolic bowl would not experience simple harmonic motion. And it bothered the heck out of me because what he just said, let's just put a ball in here and imagine it going back and forth because it matches the turning points, right? You start it here, it's going to have enough, the way the energy transfer works, it's going to cash in that potential energy for kinetic energy. It's going to slowly cash back in that kinetic energy for potential energy, and it's going to stop right here. So if you literally had a bowl this shape, it would go back and forth between here and here. So I thought, oh, this is awesome. Let me maybe go make a parabolic bowl or I can really help my students understand this. But it was in a class where we had just, like the previous week, done the brachistochrone problem. And the brachistochrone problem is, a famous problem in sort of sophomore, junior, senior level physics at the college level. And the brachistochrone is the shape of a slide. Like imagine you have some wire shape down starting from the top and going to a bottom. And it's the shape from here to here that under gravity, a bead sliding along that wire would take the least amount of time. That's cool, right? Whatever. But it turns out, does it have to? I don't think it has to. Or I'd have to think about that. But it turns out that no matter where you start the bead on that slide, it will take the exact same amount of time to get to the bottom. So that's super cool, right? Well, that's what simple harmonic motion is like. Take your spring and stretch it out as far as you want and let it go. It'll take the exact same amount of time to get to the middle. That's because the frequency of the spring is independent of the amplitude. So it turns out you need a brachistochrone for a ball to go back and forth and to have its potential energy look like a parabola. I'll say that again. You need a brachistochrone for a ball rolling back and forth for its potential energy to look like a parabola. It's crazy. It's absolutely crazy. And so this notion of rolling a ball in here, which helps the students understand the turning points, it's not the same physical problem as what is being calculated. And I was so frustrated when I realized that. So I ask you guys, how often do you use the ball rolling around in the trough to really drive home these turning point ideas? And how much does it bother you to realize, because man, it bothered me, that it's actually a different problem. The only thing it shares a few things, but the main things it shares are the turning points. So, sorry, long aside there. I'll just back them up a little bit.
Such a motion restricted like that, the period of oscillation
Oh, this is awesome.
And by the way, this is not yet a harmonic oscillation. This is just a repeating motion as I'm describing here. The period of that oscillation would be t equals 2 integral x min to x max. This updates the one I wrote up the other day. Okay. Dx root 2 over n e minus.
So, right, where does the 2 come from? Obviously, the 2 comes from because it has to go there and back again. It's really interesting, right? So, when you look at the integrand, it's clear, it doesn't matter if you go there or back, you're going to get the same answer, right? But think about it physically. Are you absolutely convinced, and I'll just use this analogy, which I just said is wrong, but are you absolutely convinced that it takes the same amount of time for the ball to roll up here as it does to roll back again, right? Ask yourself that, honestly. Are you convinced that the time should be the same there and back again? Because I don't think it's as obvious as it is when you look at the integrand. You're like, I guess this is all there is to it. So yeah, I'm convinced, right? When you look at the integrand, you look at it as a spatial integral. You're like, well, the space is the same left and right. So yeah, I'm just going to put this 2 in there. But isn't it fascinating that your gut, my gut, maybe you're laughing at me right now, that your gut is like, oh boy, do I do I really believe it's going to take the same amount of time to slosh back and forth? Now, it could be that that's the sloshing problem, right? That what I was just saying before, which is that this is a bad analogy. Maybe actual balls in bowls don't take the same amount of time going there and back. Wow. I actually don't know if I know the answer to that question. I think it does, but I'm not sure. So isn't that interesting that the two, because of the integrand shape, makes total sense. My guess is he's going to gloss over it and say really quickly, well, of course, it's the same there and back or something like that. But the physical intuition is a struggle for me.
Events. We're actually going to be working with this particular potential a fair amount this semester. Good. So that defines a period of oscillation. This is not a symmetric one. The other one I had minus A to A. Okay, we'll get back to that. But yeah, that defines a period of oscillation and just the motion back and back again, back and forth. And the plus sign was motion positive direction, minus sign motion negative direction. So good, you get the period of that motion. And what we're going to do now is talk about that general x to the nth power potential and apply all of this. That's what we were getting to last time.
Okay, I think I'm just going to stop right there because already there's been such really cool stuff. It sounds like what he's going to do from now on is do potentials where this integral might be doable, right? I got to tell you, this is a nasty integral most of the time. And so the thing I've used the most is parabolic potential energy, right? Because a parabola, wait, I said that wrong. I didn't mean parabolic. I meant the potential energy for a parabola, right? Which you approximate, I keep saying it wrong. The potential energy of a pendulum. The potential energy of a pendulum looks a lot like a parabola when it's down low, but it's not a parabola, right? And so when you stick that actual function in here, oof, nasty, right? It's really, really tough to get this. I don't even think there's an analytical solution. So this is a really, really cool approach. And I assume he's going to do some that are doable. So anyways, lots of really cool stuff in here. I love this stuff. I'm curious about what you guys think about the 6 to 3 to 2 to 1, that you'd have to do all of that work to get to being interested in the shape. He said they're going to deal with it later. So my guess is it's going to come back around again. And I'd love to hear your thoughts about the ball sloshing around analogy problems that I was talking about. All right. I thought you did a great job. I think the students get this stuff and they're motivated to really do the next steps. So I think that's super cool. All right, everybody, have a great day. And remember, physics teachers are awesome.